Hi guys, let's do count good nodes in binary tree. So we're given a binary tree root. A node x in the tree is named good if the path from root to x there are no nodes with a value greater than x, and they want us to return the number of good nodes in the binary tree. So if we take a look at this example, we're given this tree and we output 4 because the nodes in the blue are good. So root 3, or the node 3, which is the root here, is a good node because the root is always a good node. And then if we look at this path down here, so if then this 1 is not a good node because in its path there was a 3 before it, which 3 is greater than 1, so 1 is not a good node. And then 3 is a good node, this 3 down here, because in this path 3 is the biggest value that we have, right? Because it just has to be greater than or equal to. So it's equal to this other 3, but there's nothing else that's greater than it. If we go down this way, then this 4 is a good node because in this path from 3 to 4, 4 is the greatest value. So that's a good node. And then in this path, 1 is not a good node because both 3 and 4 are greater than 1. So 1's not a good node. And then in this path, 5 is a good node because 5 is the greatest number in this path. So if we count these up, then we have 4 good nodes, so we return 4. In example 2, we are given this tree and we output 3 because, so starting from the root, which is 3, this is a good node because the root's always a good node. And then in this path, this 3 is a good node because 3 is the greatest value on this path. Down here on this path, 4 is a good node because 4 is the greatest value in this path. And then if we go back this way, then this 2 is not a good node because in its path from the root to get to it, 2 is not the greatest value because we have both of these 3's which are greater. So if we count up all the good nodes, then we have 3 good nodes, so we return 3. And then in our last example, we are given a tree which is just 1, and we output 1 because we only have one node, which is the root, and the root is always considered a good node, so we just return 1. So if you guys noticed how we were doing the algorithm to count the good nodes, we're going down each path before going back and checking the next path, which sounds like DFS. So we're going to need to do DFS, and we are given the root as input, but we also need another separate variable to keep track of our maximum number that we've seen so far on a given path, right? Because when we get down, if we're going down this path and we reach this 3, then we need to know what the maximum number that we've seen in this path so far is to be able to compare it to this 3. So since we need another variable that we don't have in here, and we're doing DFS, so we're going to need to pass these variables through to the method, we are going to create a private method for performing DFS. And so we're going to have a node, and we're going to just call this int max for the maximum number we've seen so far. And then we're just going to call our helper method up here, and we're just going to return that with the root. And so when we're at the root, our maximum number so far is the root's value itself, so we'll just pass that through as our initial maximum. So then if we think about our base case, then if our node is null, then we're going to return 0 because we can't possibly have a good node if we don't have any nodes in the first place. So if our node is null, then we'll just go ahead and return 0. Okay, and then down here, so if we think about how we'll break this down, we are checking, so we need to do a DFS on the left path and the right path for every single node. So if we start all the way at the bottom, let's say we start at 3, the left path is nothing and the right path is nothing, so we just go with the node itself. But then if we go backtrack one node up to this 1, then we need to compare the left path with the right path, which is 3 and 1 to nothing and 1, right? So, and we need to check both of those. We're not comparing them. We're just checking both of them and adding up the good nodes. So we know we're going to have to add up the values that we get from a DFS. So we're going to have a DFS of node.left and our max plus a DFS of the right node and our max. But in the middle here, we're going to have to do some kind of work. So we're going to want to have a count to keep track of how many good nodes we've seen so far. And we'll set that to 0 because we're going to so basically for every single node, we're going to check if it's a good node or not. And if it is, then we'll make our count 1. And then we're going to add that count to our left and right at the end. So that way we're adding them all up. So, and the way that we check if a node is a good node or not is, so they tell us that a node is good if from the path, in the path from root to x, there are no nodes with a value greater than x. So that means that x has, or whatever our node's value is, must be greater than or equal to our max seen so far. So if node.val is greater than or equal to max, then our count will be 1 because our count is keeping track of if this node is a good node or not. And then we're also going to update max to be our node's value because that's going to be our new maximum, which we're going to pass through for each path here. So that should be it. And then our time complexity is going to be O of n, where n is the number of nodes in our tree. And that is because when we do DFS on this tree, we in total have to visit every single node in the tree once to check if it's a good node or not. And then our space complexity is also O of n. And that is because we need to add every single node that we visit onto our call stack when we do our DFS. So that is it for this problem. Thank you guys for watching. Bye.